Welcome to the Using Diamond Typing to Improve Recovery Techniques webinar. I am your organizer, Michelle Beacom, Managing Editor of CIM Magazine. My co-organizer is Ryan Bergen, Editor-in-Chief of CIM Magazine. Our panelists presenting today are Lucy Hunt and Mike McCubbing of Saskatchewan Research Council's Mining and Energy Division. We thank our attendees for joining us. Just a little housekeeping before we get started. To ensure you have optimal audio, if you are using your computer audio, make sure that the computer audio button is selected. If you are joining by phone, make sure the phone button is selected. And lastly, during the presentation, you can type any of your questions into the question box, and we will get to them during the question period at the end. Note, there will be some poll questions during the presentation, so pay attention. Now, without further ado, I am going to turn you over to Mike and Lucy.
Thank you very much for the introduction, Michelle. So my name is Lucy Hunt, and I'm the supervisor of the Applied Diamond Services group of the GLDS Diamond Laboratory.
And I'm Mike McCubbing. I'm the supervisor of the Geoanalytical Laboratory Diamond Labs. And we're going to give a bit of a presentation on diamond typing today.
So I guess firstly, what do we mean by typing? So if we're typing a diamond, what we're doing is we're looking at their nitrogen content. So that's anywhere from a few ppm to a few thousand ppm, and their aggregation state. And by that, I mean the configuration of the nitrogen atoms in the crystal lattice. So we'll be talking about how we type the diamonds, and then moving on to how this might relate to recovery. Sorry, just trying to move on to the next slide. Here we go, sorry about that. So just a bit of background on the Saskatchewan Research Council. We're one of Canada's leading providers of R&D and technology commercialization. Our Mining and Energy Division works with companies from across the world, anywhere from grassroots exploration down to mine site remediation. We also work on a range of commodities from diamonds, potash, uranium, rare earth elements, and with clients within Canada and the world. So our Geoanalytical Diamond Lab is one of the largest of its kind in the world. We have a micro-diamond caustic fusion circuit with 80 kilns and a small bulk processing plant for macro-diamond recovery, which is basically the same setup you get at a full-size mine, but on a much smaller scale. So we can therefore carry out work for companies at all stages of their mine cycle and their life cycle, really. Our Applied Diamond Services group was established a few years ago, and it was put together to basically bridge the gap between research and industry. And we wanted to commercialize techniques developed in universities. And we now offer a range of services and test work programs, which include, but are not limited to, things such as nitrogen diamond typing, diamond grading, color grading. We can look at diamond damage and breakage, as well as all gang luminescence studies, recovery techniques, and plant design. So we'll be touching on a few of these subjects in the following talk. So a brief outline of what this presentation is going to be on. Firstly, I'm going to talk about some diamond typing. So what is it? How is it done? Some of the added benefits of typing, not just in terms of processing, but then we're going to talk particularly about how this does affect the recovery of diamonds, how this might affect the flow sheet and the machinery and equipment you might put in place to make sure you recover everything. And finally, we're going to be talking a bit about XRT, which is one of the the newest advances in diamond recovery that we've seen in the last few years. So why do we care about impurities in diamonds? Well, there's a few different reasons. They can have a huge impact on a number of characteristics, anywhere from color and therefore their value, as well as the ability to recover them and therefore the technology that you require to do so. So by understanding the properties of the diamonds, you can put together the best and most efficient recovery circuit. So that's really where this talk is going to focus. So diamonds are pretty chemically boring. They are composed of nearly pure carbon, but as they grow, they do take in some impurities, most notably nitrogen, but other things such as boron can enter the diamond's crystal lattice. The presence or absence of nitrogen and boron and how it is arranged, which is its aggregation state, can be used then to type a diamond. So when we talk about type 2 diamonds, which we've seen a lot more recently in the media with these very large type 2 diamonds coming out from mines in Africa. Type 2 diamonds contain no nitrogen. If they've taken in no nitrogen but possibly a bit of boron, then we call them type 2b diamonds. And these are your blue diamonds, so obviously very, very high value. Then type 1 diamonds, these are your diamonds that contain nitrogen. In the next few slides, we'll talk about how you can further break up this group based on how that nitrogen is arranged within your crystal lattice. So to type a diamond, we use an instrument called a Fourier transform infrared spectrometer, or FTIR. And really, it's a relatively simple instrument. You fire infrared light through your diamond, and then we collect the residual spectrum after it's gone through. Diamond will absorb certain parts of that infrared light, and based on the impurities, we can then use the residual spectrum to type the diamond. So this is just an example of a spectrum that we might expect to get from our FTIR instrument. We can see that the blue part of the spectrum are peaks that are always associated with diamond. So as long as we're analyzing a diamond, we will get these peaks in this orientation and with these set proportions. And we actually use this to calibrate the spectrum. So we use the peak heights of this to calibrate the nitrogen peaks, and this will give us a nitrogen concentration. The green peaks on the right, these are associated with your nitrogen. So we get different peaks in different positions based on how your nitrogen is arranged or the aggregation state of that nitrogen. And then we get different peak heights based on your content. So obviously the higher the peaks in relation to your diamond peaks, the higher the concentration of nitrogen. So this is where it gets a little bit more complicated. So as I said, type 1 diamonds, so diamonds that contain nitrogen, can then be further subdivided based on how that nitrogen is arranged. Type 1b diamonds contain singly substituted nitrogen. So this is the first nitrogen that's taken in by the diamond as it grows. These type of diamonds are incredibly rare in nature, but typically your synthetic diamonds, those yellow diamonds that we see on drill bits, these are type 1b diamonds and contain singly substituted nitrogen. The reason that they're incredibly rare in nature is that on relatively short geological timescales, that singly substituted nitrogen will move in the crystal lattice into pairs, into poorly aggregated pairs of nitrogen, and this is what we call type IAA diamonds. Again, over much longer geological timescales, these pairs will move again or aggregate again into highly aggregated IAB diamonds, and this configuration is 4 atoms of nitrogen surrounding a vacancy. Each configuration of nitrogen atoms has a unique spectrum. So here there's just some examples of some nitrogen aggregation spectra that we'll see. So we can see type 2 diamonds contain no peaks in that nitrogen region, but we can see the very distinct diamond peaks. Type IAA diamonds, so this is 2 nitrogen atoms paired together. We can see they have a relatively simple double peak. And then our IAB diamonds, which is the D graph on the bottom right, This is your more complex, highly aggregated 4 atoms surrounding a vacancy. And we can see you get a lot more complexity in your peaks. So diamonds with 90% of the nitrogen in pairs will be classified as IAA. Diamonds with 90% of the atoms as 4 atoms surrounding a vacancy will be classified as IAB. Everything in between, so 10 to 90% of IAA and IAB, are what we say is having mixed aggregation states, and we classify these diamonds as type IAAB. So when you get your report of typing diamonds, you'll see type 2, type IAA, type IAAB, and type IAB. And those last 3 are all diamonds that contain nitrogen. So as I said, your nitrogen aggregation state and content can be used and have other advantages. So in academics, typically diamonds are typed to give you as much information as you can for them. As I said, diamonds are typically boring. They just contain carbon, so there's not a lot of information you can get. But you can use the amount of nitrogen and how it is arranged in the lattice to give you an idea of time average mantle residence temperatures. So these are the temperatures at which the diamonds were stored within the mantle. If you assume a constant and approximate geotherm, you can then give an approximate depth of residence. So this is just some example data from 2 kimberlites in close proximity. If you've worked in the diamond industry, you'll know that it doesn't matter how close your kimberlites are, they can have incredibly different diamond populations in terms of color, size, grade, and all the characteristics in between. So obviously there is some overlap between these 2 kimberlites, but you can see 2 pretty distinct populations in both. The graph on the left, we see a group of diamonds that plot from around 1050 to 1100 degrees centigrade, and then another cluster of diamonds around 1130 degrees centigrade. If we look at the diamonds on the right, we have a much closer clustered group at around 1050, and then a deeper group at around 1150 degrees centigrade that just isn't really as visible on the other kimberlite. So obviously these 2 kimberlites have had a lot of work done. So when you're going into mine and deciding which kimberlite you may want to explore first, you're going to be looking at grade. You don't necessarily care where the diamonds were sampled, you're more looking at the grade and that part of it. But when this can come in more useful is when you're in exploration. So just as a possible example, maybe kimberlite X has a population of fancy yellow diamonds, and maybe these come from this top cluster of diamonds in kimberlite X. Maybe kimberlite Y has a population of much larger diamonds, and maybe these are from that deeper depth, that 1150 degrees centigrade. So we can use this information going forward as possibly kimberlite Y, maybe your value, your cost per carat of diamonds is much higher, and this is the kimberlite that you're going to target and prioritize first. So if we're looking at newly discovered kimberlites, on the bottom we have a kimberlite with some green data, which looks quite similar to kimberlite X. On the bottom on the right we have diamond data which, although it's not a lot, does look like it has more similarities to kimberlite Y. Now obviously in exploration you don't have the cluster and the amount of data that you'd have if you're going more into producing a mine. But what we can say is possibly the kimberlite with the orange data may have larger diamonds, and maybe this is what you're looking for. So we can use this information to prioritize our targets going forward. And this is especially important if you have limited exploration budgets or you have a limited drill time. So you can possibly say this first time we're going to concentrate our money on this kimberlite on the bottom right with the orange data, as we're really hoping to find some frequency size distribution similar to kimberlite Y with this larger diamond population. So I think we have a poll question now.
Yes, we do. I'm just going to launch it now. Thank you, Lucy.
Perfect.
Just wait a few more seconds. Everybody has voted. Okay, I'm closing the poll.
Okay, so as we can see from the data of the poll question, there are some people that have typed diamonds and not everybody. And this really explains why ADS was started. It was to bridge that gap. The typing of the diamonds is typically more something that's carried out in academics, and we're just trying to now bridge that into industry. So now moving on to typing diamonds and why that is important in the recovery of your diamonds. So one of the ways to recover diamonds is XRL, X-ray luminescence technology. So you fire an X-ray at a diamond, it fluoresces, it luminesces, and this luminescence is detected by a photodetector. And it's predominantly affected by nitrogen concentration and aggregation. I've also included in this slide something about UV fluorescence, and this is really because sometimes people get a little bit confused about X-ray luminescence versus UV fluorescence. And UV fluorescence is actually the effect that long-wave UV light has on a diamond. And it's typically observed as a blue color, although you can see colors green, orange, yellow, and etc. It is relatively common. If you think about if you put your diamond under a black light, some of those diamonds will fluoresce. Approximately 30% of all diamonds will fluoresce. But this is not related to nitrogen content or type. So a type 2 diamond, for example, can have a very strong blue fluorescence, and a type 1 diamond cannot, or vice versa. It is X-ray luminescence that is really key and diamond typing, does play a role in whether a diamond luminesces or not. So again, UV fluorescence does not have an impact on recovery, but it actually can have quite a negative impact on the value of rough diamonds, with at least a 10% reduction of diamonds with strong fluorescence. So this obviously can have severe consequences in whether a mine is feasible or not. So it is something important to understand in your diamond population. It's something that will get done when you grade your parcel of diamonds, but it doesn't have an impact on recovery. Your X-ray luminescence properties of a diamond can have significant impacts on your recovery. So a type 2 diamond, so this is diamonds without any nitrogen, typically exhibit no luminescence. So this makes them unrecoverable by X-ray luminescence or XRL technology. So Mike is going to go into some details about what you need to do if you do have a high population of type 2 diamonds and some other techniques and methods of recovery that you can implement. In addition, diamonds with varying concentrations and aggregation states of nitrogen can luminesce differently, and therefore make recoverability by XRL more difficult, or you at least need to calibrate your XRL differently to recover them. So I'm now going to pass it on to Mike, who's going to talk about how diamond typing and luminescence in particular can affect your recovery.
Great, thanks, Lucy. So we're going to switch gears now and take all that good science that Lucy is doing on diamond typing and see how we can translate that into a better understanding on how we set up recovery circuits to improve the recovery efficiency and improve the productivity of the operations, and how the diamond properties play a part in simplifying flow sheets to maximize those recovery rates and reduce the yields. So diamond recovery processing really relies on those unique diamond properties like luminescence and hydrophobicity, and there's various recovery techniques that are based on those properties that we can exploit to make sure we recover just the diamonds and not the gangue material. And obviously, kimberlites being a highly variable rock type, those variations can have an effect on the recoverability and the yields. So this presentation will focus primarily on final recovery downstream of concentration, and how processing can be related to diamond types. So here's an example of a typical diamond recovery flow sheet post dense media separation. So we'll start with dense media concentrate, and then depending on the recovery circuit setup, it may or may not require drying. Magnetic separation is often used to get a mass reduction, but that can also play a part in your total mass of volume going to the remainder of that recovery circuit. That can be done wet or dry, but there's a few things that you have to be mindful of when also using magnetic separation, because you can have magnetic inclusions, and we'll get into that in a little bit. Following magnetic separation, then you're going into your X-ray luminescence circuit. Typically, the sizes will be, the material will be sized into different size fractions for setting up your different algorithms and speed and flow rates, coarse, medium, fine, and depending on the flow sheet, that can vary quite a bit. Beyond X-ray luminescence, there's often a scavenging process that's involved, and that can be, an example of that would be laser Raman or grease tables. So I'll discuss a little bit about those and how they're implemented, but they're typically very low production rates, and you don't get a lot of productivity out of those machines. However, they can improve your yields. And then finally into hand sieving and sorting, and then some of the secure handling procedures that are required to maintain the integrity of the product downstream. So we'll also be making the assumption with the remainder of this talk that the diamonds have been liberated. So lockup is a bit of a different issue when they are still entrained in kimberlite. We won't get into that today, but that could be a future topic. So again, the goal is to process high volumes with low yield and maximizing your diamond recovery. So with magnetic separation, you can measure the magnetic susceptibility of your diamonds using a capper bridge, and that will give you a determination of that threshold for high intensity magnetic separation, whether or not wet or dry. And some of the factors that can affect that include shape, size, the inclusion type, if they're iron and magnesium bearing, the abundance, and your feed rate going through the unit itself. So you can see some images on the screen of some very heavily included stones on the right that may not be as amenable for magnetic separation, where the stones on the left, no inclusions, and they should go into your non-magnetic fraction. And once you've got your measurements from your capper bridge, it'll plot something like this. So on the left, we've got your gem diamonds, and you can see they show or exhibit very weak magnetic susceptibility. It's same with some of the brown diamonds, and these are all about 4 grainer size, so fairly good size, something that you would obviously want to be recovering. Once you get into heavily included stones, you can see that variability starts to increase. And if you have your threshold set at a certain point here, as shown in the dotted red line, there can be some loss in some of those stones because those magnetic inclusions will get pulled off by that high intensity magnetic separator. So being able to understand that and know where those set points are to be able to remove a lot of the waste ore can then also optimize that flow sheet and give you a good start to that recovery circuit. Next, you head into X-ray luminescence. Right now, this is probably the most common primary recovery concentration method. It's been in use for several decades, but you do require pre-concentration because the feed rates can be fairly low, and so dense media separation is required prior to XRL. It's also very effective in the smaller stone size range. So you can get machines that are going to give you very efficient recovery rates into that 1 to 4 millimeter range. Again, dependent on diamond type, and as you get smaller, those luminescent properties then become weaker and harder to exhibit to be able to detect using the photomultiplier. Another advantage of these X-ray luminescence units is they are highly evolved. They've been around for some time, and they're proven in many operations across the world. But you can also see a highly variable yield with some of these, and in the lab, we've seen yields ranging from 0.2% to 50%. And obviously, if you're starting to generate a 50% yield, all the downstream processes then will get bottlenecked, and productivity will almost come to a standstill at that high of yield. So you have to be able to figure out what kind of background material you're working with to be able to add different types of filters or different thresholds on your X-ray settings to be able to reduce that yield and increase the productivity again. So right now there's several suppliers that provide X-ray luminescence equipment, all with slightly different criteria and feed rates. But again, calibration and setup of these machines is imperative to their success. So here's a simplified cartoon of an X-ray luminescence sorter. So here you've got your feed hopper with your gang material, some diamonds. They'll get transferred onto a feed belt or a vibrating pan feeder or a chute of some sort to then be presented in front of the X-ray tube with a photomultiplier. Behind that, you're going to have an ejection mechanism, and that can either be air or a valve or a gate. And that will then concentrate those accepted stones into a hand sortable state, and then all of the reject will then get transferred forward to either a secondary process or for coarse rejects. These can also come in several different configurations with a variety of feed presentations and ejection mechanisms. The resonance time and the amount of time the particle is exposed to the energy source can also vary depending on the equipment manufacturer. So that can also add to the need for understanding of the properties of the stones. Your yields obviously can also be affected by the threshold of the X-ray sending, so you really have to try to find a balance. One thing that can give you some more information on how to set up these X-ray luminescence units is to do a luminescence study. So you can determine the recovery potential of a population of diamonds by using X-ray luminescence, by measuring the index of those stones and determining what percentage could exhibit poor recovery potential by X-ray luminescence. So you'll classify them in their luminescence categories as high, moderate, low, very low, and not recoverable. And that will relate to diamond type in a certain extent, and we'll get into an example of that a little further on. So you'll document that diamond's decay time as recorded by the unit that we use for generating this data, which is a POLIS M. So we'll pulse that individual stone and get a curve to determine exactly what the intensity of that luminescence is presented by that stone. So here's an example of that curve that will be generated. So the diamonds are pulsed with the X-ray to measure the response and plot the peak intensity as illustrated on this bell curve. And so you'll have that peak intensity at a certain wavelength, and you'll be able to measure that, and then from there you can calibrate your X-ray unit accordingly. So here's that same bell curve, and you can see in the pink dotted line, that's an example of a diamond. But then you also have your gang material, and some gang material can also present itself to the X-ray unit in a similar fashion, where it can have a certain wavelength in a similar scheme as the diamond, but it may not exhibit as high a threshold, or as high of intensity. And so you can see in this example, here's a zircon, where it has a couple of peaks within that range, same wavelength as the diamonds, and same thing with calcite, where it can also present a peak. And so if you have a deposit that has a lot of calcite or some veining or a system within that kimberlite, it can then present a problem in your downstream recovery and increase your yields with the material that's going to the final sorting. So to help alleviate that, you can add filters. And so these rectangles here are filters that you can insert into that machine to then mask those response times from the unwanted minerals. But again, it's a matter of what wavelength that you need to insert those filters in to be able to still detect the diamond intensity. Another unique property that diamonds have is what's called rise time or decay time. So once they're presented under the X-ray, if you think of it as an incandescent light bulb, it takes a small fraction of time to reach that peak intensity. So here's an example here where if you turn the X-ray on, you'll have a fast component where it'll immediately start to luminesce and then slow down until it reaches that peak luminescence. If you turn that X-ray source off, then there's also a decay time where it will also drop off in that intensity, and then that diamond or filament in an incandescent light bulb example will then burn out again, then increase again if you turn that X-ray on that same type of curve. The advantage you can use is you can also use that as a filtering mechanism, because that related to your gangue material, where you turn your X-ray source on that gangue material and it'll be at peak intensity as soon as that X-ray source is applied, and you won't have to wait that certain amount of time to be able to detect that. So you can set up your algorithm to then detect that diamond based on that decay. And so rather than detecting it while the X-ray source is on, you wait for that half a second while that X-ray source is off to determine that luminescent property to then filter out any of the unwanted gangue material. So here's another example of some rise times in some +11 or 3mm diamonds. So this is an example of a threshold. And so if we set that threshold at 5 milliseconds, anything with a longer rise time then that 5 milliseconds is going to be less recoverable. So longer rise times, upwards of 50 milliseconds, can lead to poor recovery potential. And maybe 50% of the stones shown in this example would be beyond that threshold. That way they wouldn't present themselves to the X-ray unit properly. Here's another example of luminescence this time. So low luminescence below a recovery threshold, here shown in the red line, can also lead to a poor recovery. So lowering your threshold, so if we drop this down to 500 or 250, that's also going to increase your yields. So you also have to find that balance of what's where the value retains. So if you see a majority of your stones that are low recoverability or low luminescent, and they're in the smaller size ranges, but you are increasing your yields to recover those small stones, that's a decision that has to be made. But without that information, you can't make those types of decisions. So when you put it together with these luminescence studies, you can exhibit the low luminescent in the orange, the non-recoverable stones based on a certain threshold setting, very low luminescent stones in the yellow here, some moderate or low luminescing stones in the blue, moderate, and then high luminescing stones. So as this, here's an example of two recovery thresholds where 80% of the stones may not be presenting themselves to the X-ray source in the right manner to be recovered right away without any type of filtering or increasing the intensity of the unit itself. And that can produce high yields and slow down productivity.
Okay, I think it's time for our next poll question, Mike.
Yeah.
Okay, I'm going to close the poll now. Here are the results. And back to you, Mike.
Okay, so now we're going to look at an example where diamond typing has come into play to understand the population, which can affect the recoverability and the type of setup that you use for your diamond recovery circuit. So here we did 477 +11 stones from the Pence unit of the star kimberlite. They were assessed for their luminescence characteristics and nitrogen aggregation. So they were also typed and did the luminescence intensity studies. The population as a whole shows a normal distribution data set with a mean of 1,536 millivolts. So a little bit better than what our recovery threshold is if we set it at 500. As we move into the diamond types, you can see that those histograms, they change. So the luminescence histogram of the type IAA, the diamonds are normally distributed around the 1,000 millivolt level. The diamond histogram of type IAB, they are sitting around the 2,000 millivolt level. And in the type IAB, they're around 4,000 millivolts. But then here is where it becomes interesting. And this is the non-aggregated nitrogen, the type 2 stones that are essentially nitrogen free. And they're showing much less response in the luminescence response. And where they're down to that 250 or 500 millivolt level. And that's hinging on that line of where your threshold would be with that X-ray luminescence unit. So just based on typing alone, we can already surmise that the recoverability of these type 2 stones, which could potentially be of higher value, is going to be increasingly difficult. So now we look at this in contrast to the rise times that we have with the type 2 bearing stones. So they have considerably longer rise times than the type 1, the nitrogen bearing diamonds. So you can see the total number of stones, the maximum response times, the minimum response times. And what this shows us is the type 2 recovery can then become a twofold problem where they exhibit low luminescence, but they also take a longer time to reach their peak luminescence. So even if they are presented to the X-ray source and given enough time to luminesce, that luminescence curve is going to be weak and show a slow rise time to then get up to that weak peak luminescence, adding to that complexity for recoverability using XRL. So this is when it becomes important to have a scavenging technology to then increase that recoverability again. Again, like I said before, they typically low throughput, but they are going to be very effective at fine diamond recovery because of that low throughput. We use a grease table at SRC for our downstream processes for our scavenging on our circuit. And we find it works very well, but again, it's hard to scale up, and then it also becomes fairly operator heavy. And there's a lot of variables with grease that are less attractive, with it being obviously less secure. It is more of a hands-on process, and if you get into automatic grease belts, they become maintenance heavy. Laser ramen, again, it's very effective where it can produce a very clean concentrate where you're only sorting diamonds, but again, it becomes a very slow process, restricting and potentially bottlenecking your circuit. So this is where X-ray transmission then comes in. It's not necessarily new, but it is evolving. And so it's a different technique that they use for X-ray transmission recovery, and it's based on atomic density. So rather than looking at the luminescent properties of the stones, it's looking at a measurement of X-ray absorbance. So it's really indiscriminate of diamond type. And so we're going to look at how this algorithm works. So as it's presented under the X-ray source, it'll produce this image on the left here, where it'll take a measurement of that density or that X-ray absorbance, and then the algorithm will look and convert that into a false color image. So anything above a certain threshold will be marked as blue, anything below that threshold will be marked as red, and then to the final processing to then activate a mechanism for ejection. So here on the far left, we've got the raw XRT image. So in detail, you take a backscatter image of that X-ray source. Here's the classified, so you see all the blue particles, and then it identifies one red particle, which would then be classified as a diamond, to then eject the eject the control valve to use an air actuator to eject that diamond into a concentrate. So XRT is used in a lot of operations, and they're continually getting uptake in existing brownfields and pre-development stages of operations. But it's still a pre-concentration unit prior to DMS. Advantages of that is you are taking coarse stones out prior to crushing and eliminating or reducing the risk for any diamond breakage. They are very high volume, but there are limitations to the size fraction that you can introduce to them with the current technology. But you can see at the top size greater than 150 millimeter or 100 millimeters, you can get upwards of 250 tons per hour. Even in the mids range at 75 tons per hour, this is pretty high capacity and kind of field ready installation for any mining operation. As you get into the fines, obviously the recovery productivity goes a little bit down, but you're still exhibiting a high yield, and so any test work that we've seen, we're getting yields of less than 1%. The nice thing about XRT is it seems to still be an improving technology, and because of the optics and the sensor bars that are included, that are inside the XRTs, the sensitivity of these things is increasing, and as that increases, the number of pixels then increase, which can push those resolutions down to those finer size fractions. But with that, you're also introducing more particles. And as you introduce more particles, that's just a number, exponentially high number of calculations that then it has to make, or decisions it has to make on what to eject. But that's exactly where the technology is moving. And so there's numerous suppliers on the market that are offering XRT technology. You do still have to do some calibration to these units to determine exactly what that density threshold will be for detectability based on your background mineralogy. So there is some setup and calibration that is required, and it's not quite yet a full replacement to DMS. So there still has to be some evolution in these X-ray transmission units, but you are increasingly seeing uptake in industry with this technology. And what that can allow you to do is simplify your flow sheet. So if you've got that high volume, low yield that you're looking for, you can still concentrate using dense media separation, but now you're only putting those fines through potentially a newer technology XRT unit. You may or may not need this laser Raman or grease table scavenging technology once the resolution can get down to these finer size fractions. Again, that really cleans up the flow sheet and then allows you to reduce diamond breakage and become a lot more efficient in the way that recovery circuit operates. So in final summary, so the additional characterization work can provide details on the variation between diamond parcels and can assist in recovery or plant design, and also give you a really good understanding on that diamond parcel and how they can be highly variable between units or between different kimberlites, even in the same field. They can provide feedback on the geologic variance, and then obviously if you can introduce XRT in your process stream, it can have a number of benefits. One, lower cost to build, operate, and maintain. Obviously, reducing diamond breakage. They can be with less moving parts. You can improve security, and and the added benefit of doing all that is improved safety.
Okay, I'm going to launch the last poll question. And I'll give another few seconds. Okay, I'm closing the poll, sharing the results. Okay, I'm hiding the results, and we're going to start the question period. Mike, I'm going to put you back on camera.
There he is. Back, Mike. So yeah, we have a question for you. Do you suggest testing? Oh, sorry. Before we get into that, I should just remind everyone that you can in the control panel on the what should be the right-hand side of your screen, you can type in questions for the panelists. And we have such a question. Do you suggest testing on separate geological units as well?
Want to take that one?
Yeah, I can do. Yes, I think that is important, especially at the start. I think we're kind of lucky where we are because when we process diamonds, they often come in batches associated with different lithological units, different kimberlites, etc. So we can do testing that is still very broken up into lithological units. We can then categorize the diamonds in terms of shape, color, and that side of it too, and then we can type. So we can really get a really good handle on whether your population of diamonds is consistent down your whole kimberlite, whether you might see any problems arise in processing as you hit certain units or certain depths. And this is all really important information going forward. Basically, once diamonds leave us, they're typically rolled into one parcel, so that's not always possible once the diamonds have left us. But we are at a unique stage in the process to be able to give you that added level of complexity and more information. And I think it is important, and I think it can only help moving forward.
Thank you. So can typing be done on micro diamonds?
Yes, it can actually. We've gone down to about 106 microns, although we kind of like to hover around, the smallest we go is around 150 microns. And this can have important implications in exploration if you're looking for kimberlites of possibly with more type 2 diamonds, or trying to understand whether a certain kimberlite is related to another one, etc., etc. So we have done a lot of typing on microdiamonds and how that relates to the macrodiamond populations as well.
Okay, great. Someone asked, why does UV fluorescence devalue diamonds?
It kind of depends who you ask.
yeah, that's a valid question. And I don't know if that's one for this particular topic, but that's more downstream. So that's beyond an exploration or evaluation tool. That gets more on the sales and marketing side.
Okay. What is involved in testing kimberlite ore on XRT?
So with the test work on XRT, again, it's a matter of measuring that density threshold. So again, with kimberlites being a highly variable rock type, they can have other mineral constituents in there with high density material. And so what you also want to do is to calibrate that unit to make sure that you've got that density threshold somewhere in the middle of that region of the predominant bulk material and where the diamonds lay to then again manage your yields and get that to an efficient cut point. The nice thing about it is diamonds are, again, that kind of technically boring chemistry where they are pure carbon. And so you do get any hydrocarbons or any kind of pieces of plastic that'll get picked up, but those can be removed with alternative methods other than XRT.
Great. Well, thank you, Mike and Lucy.
That's all the questions?
That's all the questions.
Okay,
Yeah.
that's all the questions we have. If you think of a question later on, their email addresses are on the screen. And we'd just like to thank everybody for joining us. Thank you to Lucy and Mike Please fill out the short survey that pops up on your screen at the close of the webinar. A link to the video recording of this webinar will be emailed to you later this afternoon. As well, the video will be available on the CIM magazine website and on the SRC website. The whole series will be available on both sites. And thank you very much for joining us for the Diamond webinar series. Thank you.
Thank you.
Bye.
Thank you.